They just built a new form of AI, and it's better than LLMs. Imagine an AI that doesn't waste time generating words, but understands meaning directly. Sounds like science fiction, right? What if I told you this AI already exists and it could outperform even the most advanced large language models in video understanding, classification, and real-time reasoning? Today we're diving deep into VLJA, Vision Language Joint Embedding Predictive Architecture, a revolutionary system developed by MetaPair, led by Yan Lun and his team. This isn't just a faster or bigger language model. VLJA represents a completely new approach to intelligence, one that predicts meaning directly, rather than relying on words. Once you see how it works, you'll understand why this might mark the end of the traditional LM era and the start of something far more powerful. Why traditional AI struggles. To appreciate the magnitude of this breakthrough, we need to understand the problem with today's vision language models. Most multimodal AI systems function in the same way. You show them an image or video, ask a question, and they generate text one word at a time. That's how image captioning works. That's how visual question answering works. And while it works, this method has hidden inefficiencies. First, these models waste effort learning things that ultimately don't matter. Consider a simple example. What happens if I flip the light switch down? A human immediately understands that the light turns off, the room gets darker, and the lamp goes dark, all describe the same outcome. For a token-based model, however, each sequence of words is completely different. It must memorize every phrasing, word choice, and sentence structure, training endlessly on superficial differences rather than true meaning. Second, token-by-token generation is inherently slow and inefficient for real-time applications. If you are processing live video, working with robotics, or trying to interpret inputs continuously, you can't understand the model's output until it finishes generating all the words. This adds latency, burns computing resources, and makes selective updates almost impossible. VLJA approaches the problem in a fundamentally different way. Instead of generating words, it predicts semantic embeddings, continuous vectors that encode meaning. Words are no longer central to intelligence, they are optional outputs. The AI first understands what something means, and only produces language when needed. The architecture of VLJA. VLJA's design is elegant yet revolutionary, built around four main components that work together seamlessly. The first is the visual encoder, which compresses images or video sequences into a set of visual embeddings. Think of these embeddings as tokens. But instead of discrete symbols like words, they are continuous vectors representing the essence of what the AI sees. For this, the system uses VJEPA2, a self-supervised vision transformer with 304 million frozen parameters, ensuring that visual understanding remains robust during training. Next is the predictor, the heart of VLJA. This module takes the visual embeddings and a text query, like a question or prompt, and predicts what the answer embedding should look like. Built using transformer layers derived from a Llama 3.21b, the predictor operates without causal masking, meaning vision and text can interact freely. Unlike traditional LLMs, it doesn't attempt to construct sentences, it only tries to predict the correct semantic representation. The Y encoder transforms the target answers into embeddings during training. These embeddings capture meaning, not exact phrasing. Finally, the Y decoder is rarely used. It only comes into play during inference if a readable text output is required. Most of the time, VLJA operates entirely in semantic space, freeing the model from the inefficiencies of token-by-token text generation. During training, the AI is presented with a visual input, a query, and a target answer. The Y encoder turns the correct answer into an embedding, and the predictor attempts to replicate it. Loss is computed directly in embedding space, not in token space. The system naturally organizes similar meanings close together and separates dissimilar ones. Instead of memorizing words, it learns ideas. Performance that shocks. VLJA doesn't just look different, it performs differently. When compared to a token-based model with the same vision encoder, same resolution, same batch size, and same number of training steps, VLJA required only about half the parameters to achieve comparable results. Early in training, performances were similar, but as the dataset grew, VLJA began to pull ahead. After 5 million samples, it reached around 14.7% CR on video captioning, while the token-based model lingered around 7.1%. Classification accuracy jumped to 35% compared to 27%. This gap did not close with further training, demonstrating a structural advantage rather than a lucky optimization. Inference is where VLJA truly shines. Continuous embeddings enable a technique called selective decoding. Instead of generating text at fixed intervals, the AI monitors semantic changes. If the meaning remains stable, it doesn't generate anything. Only when significant semantic shifts occur does it decode. For 6-minute videos averaging 143 actions, VLJA decoded only once every 2.85 seconds, achieving the same performance as a model decoding every second. This is a 2.85x reduction in expensive computations, achieved without fancy memory hacks or caching tricks. A versatile AI without complexity. Unlike traditional systems that require task-specific heads or separate models for classification, retrieval, or question answering, VLJA handles all these tasks with a single architecture. For classification, it embeds candidate labels and selects the closest match. For text-to-video retrieval, queries are encoded into embeddings, and videos are ranked by similarity. For discriminative visual question answering, candidate answers are embedded, and the nearest one is chosen. One model adapts naturally to multiple tasks, demonstrating unprecedented flexibility and efficiency. Benchmark dominance. Despite being smaller and trained on fewer samples, VLJA outperforms models like CLIP, SIGLIP2, and Perception Encoder, some of which trained on tens of billions of samples. After supervised fine-tuning, VLJA approaches specialist systems fine-tuned individually for each benchmark. On visual question answering, it excels in compositional reasoning, complex counting, and hallucination detection. On world modeling, predicting the action causing a transition between images, it achieves 65.7% accuracy, setting a new state of the art and surpassing even larger vision language and frontier LLMs like GPT-4, Claude 3.5, and Gemini 2. VLJA doesn't dominate every task, and it isn't trying to replace language models entirely. Token-based systems still excel at deep reasoning, planning, and tool use. But for perception-heavy, real-time problems, VLJA is not just better, it's naturally suited to the challenge. Why semantic understanding changes everything. By predicting latent meaning directly, VLJA removes a huge layer of inefficiency. Words become optional outputs rather than the core mechanism of intelligence. The AI now organizes knowledge around ideas and actions rather than memorizing sequences of text. Subtle changes in semantics, such as swapped attributes or altered relationships, are immediately recognized. This capability is vital for real-time systems like robotics, smart glasses, or autonomous navigation, where understanding context is far more important than generating verbose descriptions. Ablation studies confirm the architecture's robustness. Removing large pre-training or simplifying the training objectives leads to clear drops in performance. Strengthening components that support semantic learning improves the model consistently. This is exactly the kind of behavior you want from a system that aims to scale efficiently and learn robust representations of the world. Implications for the future. Velia represents a glimpse of a future where AI doesn't merely describe the world, it understands it directly. This has profound implications for industries reliant on perception-heavy AI. In augmented and virtual reality, devices could interpret scenes and provide context instantly without relying on slow textual pipelines. In robotics, machines could reason in real time, adjusting behavior seamlessly as environments change. Video analytics for surveillance, sports, or healthcare could become dramatically faster and more precise. Even everyday technologies like smart glasses could interpret and summarize the world in real time, becoming genuinely intelligent assistants. This is not just a better AI model, it's a new paradigm for intelligence, one where the center of gravity shifts from language to meaning. The AI doesn't need words to think. Words are optional, a byproduct of understanding. VLJA shows us a future where AI thinks in meaning, not words. It learns faster, operates more efficiently, and adapts seamlessly across tasks. Traditional LLMs will still be useful for reasoning and planning, but for perception, real-time understanding, and continuous interaction with the world, VLJA may already be the superior choice. The era of predicting meaning directly has begun. Are we ready for an AI that doesn't just narrate the world, but truly understands it? If you want to stay on the cutting edge of AI breakthroughs, subscribe, hit the bell, and join us as we explore the next frontier of intelligence unfolding right before our eyes.